Now I'm taking it from a smaller volume, passing it through a combustor here, where I added heat. That's essentially how I'm getting that energy from heat to expansion, bless you. And from there, that's where you're getting your thrust. You're heating up that gas, and by heating up that gas, you're essentially getting a significant amount of thrust through the turbine, which is work. The turbine is there just to extract that velocity expansion that you're getting out of the combustion. So we understand primarily how to do compressors, how to do turbines, but here when we solved the problem, what we treated it as a heat exchanger. Now, we don't want to do that as propulsion engineers. We want to actually determine how do we get that heat, and that's what we're going to focus on in the next couple of lectures. Essentially, first, we have to use a what we call combustion process. We have two species of some sort, which is essentially your fuel and air or whatever oxidizer and fuel that you're going to be using in general to burn to produce that heat. So that's a precursor for what we're going to be talking about today, so I need to be able to compute this Q. How do I go and compute this Q that we got last time? And from there, there's two sort of fundamental aspects that we need to learn before we actually compute that Q. First is, how do species or gases or fuel-air mix in general? So, gas mixtures. And the other one is, well, now that I have a mixture, I need to burn it. So how do I add that heat? Once I know the mixture composition that I have, how do I go and burn it? So that's what the couple lectures or so are going to be on. So we'll start first with gas mixtures. So you understand why are we doing what we're going to be doing.
Thank you.
So ideal gas mixtures. So this is actually chapter 2 in the book. And actually, you've seen it before. It's not the first time you see this. It's also in the thermodynamics book, Sinjil and Boyle's.
Turn off the backlights.
Oh, sorry, yes. Thank you for reminding me. It's chapter 13. So, if you have your thermodynamics book, it's actually better to, why is this so bright? Better? So, if you have the thermodynamics book, it is actually very extensive in that chapter. So, in the propulsion book, it assumes that you already are very proficient in thermodynamics, so it jumps in quite a bit. But if you want a rehash of it, in the thermodynamics book in chapter 13 is very good. Now, somebody raised their hand here.
There's for the lights.
Oh, okay, thank you. Just tell me about it earlier. Sorry. Okay, questions?
You don't cover chapter 13 till Thermo 2. They don't cover it in Thermo 1.
Well, you have it. I'm going to go over it anyway.
Okay.
So I'm reviewing it. My point is, just, you have the book, right? You could use this book to review, to look at it, but I'm telling you, it's actually more descriptive in the thermodynamics book, if you want to use it as a reference. But I'm going to be giving you all the equations, all the fundamentals. I'm going to review it right now, so you're not going to be not knowing anything about it. All right, very good. All right, so let's take that assumption where we have some container of some sort, where I have a barrier right here. You must have seen this in thermo. And you had gas A and gas B. So no moving at all fluids. The pressures are equal, P1. We've got some barrier right here. And we're going to remove the barrier. And allow gases to mix. So it's very important right here, non-reacting. Later on, we're going to do the reacting. But right now, we need to understand the non-reacting first before we jump into the reacting. Okay, so what happens? Well, from conservation of mass, the mass of gas A plus mass of gas B is going to equal to mass of total. So how do I characterize each specific ratio of each gas? Well, what we call is mass fraction. You've seen mass fraction in thermo?
Yes, yesterday.
Yes. So although you might have not realized it's chapter 13, or they might have not clearly said it's chapter 13, but that is what chapter 13 is, mass fraction and mole fraction. So we're going to go review it anyway. So mass fractions, we say, well, the fraction of gas A in terms of mass relative to M total. Very, very self-intuitive. And the same thing with B, mass of gas B over M total. That's a mass fraction. So we could write a generic form for it and say, well, Y of species, this is the species, or gas, is equal to Mi of that species over M total. And since the M total is equal to the summation, essentially the multiple gases, so Mi, starting from I equals 1 to I equals N. So if I have a whole bunch of gases right here, it's just the mass of the whole gases, then I could write a very generic form, which this is the one that we want to sort of utilize. M total is equal to the summation of I1 and the mass fraction. And what is this equal to? If I sum them all, I mean obviously M total, but if I divide it by M total, what am I going to get? It's the whole, right? So from M total, I'm going to get this is equal to 1. Because I summed the different fractions, right? If I sum this, YB and YA together, they have the same, bless you, the same denominator. And the numerator is going to be MA plus MB. Right here, I'm going to write it right here. If I sum N equals 1 for YA, it's equal to YA plus YB. If you take MA over M total plus MB over M total, let's see, what am I going to get? This is a common denominator, so these sum together, it's equal to M total. What am I going to get? It's just 1. So based on the definition of M total, this is the sum of all mass fractions is equal to 1. It has to equal to 1. Okay. So that's mass fractions. Now, we could also do this and also use moles or moles basis. Bless you. So mass, think of this in terms of kilograms. Now we want to use how many moles of that species are we using. Now for moles, we need to relate the number of moles relative to molecular weight. So mole fraction we'll say Na is equal to Ma over the molecular weight of the species A. And NB is equal to NB over molecular weight of the species. These are number of moles. Moles. So to get the mole fraction, I just need the fraction of the number of moles relative to the total. Well, it turns out that Na plus Nb is equal to N total. Same principle like we did with the mass, the number of moles. If I have 2 moles of oxygen and have 1 mole of hydrogen, well, the total summation is just some number of moles. So from there, my mole fraction, XA, is going to equal to NA, as we kind of predicted, N total, and XB equals NB over N total. So you can see the similarities here. For mass fraction, it was Y, MA equals M total. In this case, it's number of moles relative to the number of total moles that I have. So it's the same thing. It's just each, let's say, carbon has a specific weight to it in terms of kilograms, in terms of units. But I could treat it as 1 mole, 1 carbon mole, rather than its actual absolute unit. So that's the difference between moles and masses, right? You've seen mole fractions before, right? Sure. Well, we're reviewing it right now, so just memorize it. So, based on this, I could write the general form for mole fraction. I will say my mole fraction is some xi equals to ni over n total. And for number of species, if I have n total is equal to the sum of the multiple moles that I have. So ni of each species that I have. I'm going to do an example, so don't worry. Just let's list the equations so you have them, and then eventually we'll look at the examples. And what else do we cover? Now total sum of the mole fractions they have. So the summation of all mole fractions that you have is equal to same exact thing. The difference between them is this was in terms of mass, in terms of kilograms or grams, the units that you're used to in general. This is saying, well, I don't want to keep bookkeeping the mass of each species. So let me just name that species. If it's carbon or oxygen or hydrogen, I just want to focus on the species itself. How many moles of hydrogen do I have, or how many moles of carbon do I have, rather than saying it's 32 kilograms of this much. So it's kind of interesting because we always debate it at Pratt and say, which one do people really like? And if you're familiar with the systems, which one? Can you raise your hand if you like the mass fraction method? You're going to get the same answer if you use either. So only 3. How many of you like the mole fraction? Okay, we got 100, supposedly 125 students here, and we only got less than 10. It's fine. So again, one is using the kilograms and grams, and the other one is using moles. Do you have a preference in which one you want to use?
Kilograms.
Mass?
Yeah.
So we debated about this at Pratt, and most engineers like the mass one. So I'm going to ask you, I guess, after 3 weeks, once you start doing problems and things like that, which one do you prefer? You're going to be doing both. But which one you would prefer, and most likely, I think, the majority are gonna say mass. But chemists, they like the mole fraction. So that's what happens. So when you get certain people that are on the chemistry side of things, in terms of species and reactions and all that, they prefer the mole fractions. You will understand from solving the problems that sometimes it's easier to do the mole fraction than to do the mass fraction, just because the mass fraction means you have to bookkeep every kilograms or grams, rather than just saying it's this much moles. So that's the benefit primarily. Okay, so moving on to mixture properties. So molar mass, or molecular weight, MW, total, is equal to M total divided by N total, by definition like we did earlier. And that is equal to the summation of each individual mole relative to the molecular weight of each individual species divided by the number of moles itself, because I just decomposed this based on the equation that we just written. And from there, cancel out what you're gonna get is the summation of your mole fraction multiplied by your molecular weight. That's for the total. So MW total is equal to summation of each individual mole fraction multiplied by each individual molecular weight. And it's from the definition that we just created. Now, another aspect that I have to deal with is ideal gas law. Now we know the ideal gas law, which you've written in multiple forms, E equals rho RT, or PV equals MRT, or P specific volume is equal to RT. Knowing that rho is equal to M divided by volume, and the same principle as the specific volume is equal to 1 over density. Now, typically, you've taken the ideal gas constant to be constant. Now, when you have different species, things change throughout. When things change, that means you have to account for that universal gas constant. I will get to your question. Give me a second. So that's essentially R. This R is equal to the universal gas constant divided by the molecular weight, which is in terms of total. So universal gas constant, RU bar, is equal to 8.314 kilojoules per kilomoles Kelvin. But we have to remember that before, you pretty much took R, even in high-speed aero, I think you might have taken R as a constant, unless you've taken the CPs and CVs into consideration and recomputed it, but most likely you've taken R as a constant, well, in general. However, in this case, it is not constant, because as you mix different species, that changes. The universal gas constant is constant. You substitute it in there, and if you know the molecular weight, the total molecular weight, or the molar mass, then you just divide it by the molar mass, and you get that R for the mixture that you have to deal with, whether it's air with fuel in this case, or so forth.
That's the same thing.
And we got a question in the back?
Yeah.
No, it's volume and not specific volume. Anything specific is within mass.
Second to last, this one?
Yeah,
Yeah,
it's
those.
the
Row.
total on the
Mass
bottom.
over volume.
Yeah, it's
volume.
sum of each individual line.
Yeah.
Yeah, no, but
Divided by.
total on, for.
On the denominator.
Yeah.
Yeah, so think of it this way. Sum.
No, but it's UO and I, it's supposed to be N total.
Yeah, but what is the sum of n I?
It's the
Like
sum of all
PV equals LT divided
Which is
to the other side.
n
V
total.
over
This
M.
becomes,
V over M is the same
n
thing
total.
as 1 over M,
right?
which is PV equals RT.
Is that clear for everybody?
Yeah, it's all you want.
It's a sum of everything on the numerator and denominator. But this is n total. Right here. Right here. I just didn't, I'm not gonna keep putting n and I here and separate them, it just becomes too cumbersome, but everybody's clear on this? All I did was just separate them, okay? In the end, this is the equation that you're gonna use. I'm just showing you the derivation of it, it's straightforward. Questions thus far?